Okay, all these double angle formulas that you'll see on your identity sheet right under your sum and difference formulas, there's a reason they're right under your sum and difference formulas is because they're derived from your sum and difference formulas. So I'm going to go through how they came about, and then we'll look at how we are going to use them to do just some substitution as well as bringing back some right triangle trig. So the double angle formula for sine, if we were to substitute into the sum formula for sine, so this is sine of a plus b or alpha plus beta here um, that we have, if we were to substitute in beta, that would look like, oh, put this one work, sine beta plus beta, which if we put some formula, that's going to become sine beta cosine beta plus cosine beta sine beta. Since I'm using multiplication, this can be written as sine going first. Here, this can be rewritten because if you're multiplying 3 times 4 or 4 times 3, you still get 12. And then I get 2 sine beta cosine beta, which is equal to sine of a double angle. You're going to see this on your sheet as sine 2u, which is equal to 2 sine u cosine u. So the double of an angle. So if you're talking about 15 degrees, so the sine of 2 times 15 would be the sine of 30 degrees, which would be the same as 2 times the sine of 15 degrees times the cosine of 15 degrees. So that is going to work. We're going to see those and how they're going to relate into the unit circle, but this is how we got these double angles, was by using the sum formula. Similar for cosine, we can substitute in for the cosine of the sum of two angles. If we're talking about it being the same angle, then the cosine of beta plus beta would be cosine beta times cosine beta minus sine beta times sine beta. And this is just the sum formula for cosine. When cosine and cosine are being multiplied, I get cosine squared minus sine squared beta. And you'll see that this is one of your options for your double angle, or on your sheet it says cosine 2u like that. So this is one of the options that you have for your double angle for cosine. Now cosine has multiple double angle options, and that is because you have these squareds here. So as I'm starting with just cosine squared beta minus sine squared beta, well, this can become something else. You'll see that there's one that has number 1 with sine and a number 1 with cosine, because you can use those Pythagorean identities. So I can substitute in 1 minus sine squared for this cosine squared minus sine squared. I end up with 1 minus 2 sine squared, which is also cosine double angle that you see on your sheet. Okay, you can do the same thing again. How we get that cosine one, cosine squared beta minus, and I put in 1 minus cosine squared. This negative distributes to give you cosine squared beta minus 1 plus cosine squared beta, and that's where we get that 2 cosine squared beta minus 1, which is the cosine double angle yet again. So now we've got these 3 options for using this. So now when you think back to some times when you might have seen cosine and sine with subtraction, and you asked me, oh, can I just say that that's 1? No, it's something else that we're dealing with here. Same with when we have 1, and then you maybe had this subtraction with sine with a 2. We've seen these ones kind of come up before, and we haven't been able to just put it as something else. So now we're going to be able to use those. The last one is tangent. Now, we haven't done a ton with the tangent sum formula just by design, and we won't do a lot with this double angle one either, but this is how it came about, was by putting these two together. So tangent, and this says tan beta plus tan beta over 1 minus tan beta times tan beta. And this should be pretty easy to see on your sheet. This becomes 2 tan beta over 1 minus tan squared beta, and that's your double angle for tangent. Again, we don't use, just like the sum formula, we don't use this one all that much. These ones up top are going to be your big ones that we're going to see with sine and cosine. So if we move on to some examples here, similar to your sum and difference formulas, we're kind of looking to see, what is this? So is this sum and difference? Is it one of our double angles? So is it sine double angle? Is it cosine double angle? If it doesn't have tangent, we're not really concerned with that. So we're trying to think, what does this look like? Well, it looks like that first double angle formula that we have, where now u is equal to this 15. So this is going to become cosine 2 times 15 degrees. 2 times 15 is 30, so the cosine of 30 degrees. Now you're going to use your unit circle to get this value, and that's going to give you rad 3 over 2 as a final answer. Same for this. I'm looking at this. Is it a sum and difference? Is it sine double angle? Is it cosine double angle? What am I looking at here when I see sine and cosine being multiplied with this 2 in front? It's going to be that sine double angle. So this is going to be sine 2 times 15 degrees, or the sine of 30 degrees. And the sine of 30 degrees is going to be 1/2. Okay. Here's that tangent one, and we won't really see, I'm not going to put tangent on the summative. There's too much other stuff to do with sine and cosine, but this is just an example of what happens here, and this has got to be our tan double angle because it's got tangent, or it's got to be tan sum and difference when we see this fraction here. So what I see on my sheet is this looks the same as tan double angle, which means I've got tan of 2 times 45 degrees, or the tangent at 90. Okay, I have this on here to just talk about this once again. The values at 90 are 0, 1. So we've got cosine and sine. Well, tangent is equal to sine over cosine. So this is going to be 1 over 0. So you can put that in, and you should recognize that this is undefined here, that this is, that you can't divide by 0. The last one brings in some right triangle trig, which we can talk more about how this can fit in for some other stuff, but you have to remember some things from this part right here, especially from semester 1. So if sine of some angle is 4 over 5 and lies in quadrant 1, excuse me. So I'm looking at this angle here, x, that has got to be in quadrant 1 here. Okay, it's making some angle, and it's saying that the sine of that angle is going to be 4 over 5. So this is a fraction here. You could consider that to be this side of the angle. Sine is always talking about the y values. But typically when we see a fraction like this and not just a singular value like 1/2, well, I guess, yeah, you could do it like that as well, but that we're not talking about directly in the unit circle. So not direct unit circle values. It still lies within this angle, will still be between 0 and 90 degrees. We're now talking about this side and the hypotenuse. So now we're bringing back that SOHCAHTOA idea here, where we have the opposite side for sine over here, and we have the hypotenuse. You can use the Pythagorean theorem to get this other side length if we need it. Let's see what it's asking us to find. It says find sine 2x. So sine 2x, that's my double angle formula. That means I need sine and I need cosine. So I can start to fill in part of this. I have sine x given to me as 4/5. The problem is I don't have a value for cosine, but I should be able to get it. According to SOHCAHTOA, I just need this adjacent side right here, which some of you might remember. This is going to be 3. This is a 3, 4, 5. So we'll see some of those Pythagorean triples come back. If you forgot, you can always do 5 squared equals 4 squared plus b squared and solve to get 9 equals b squared and 3 equals b. So now I get cosine equal to adjacent over hypotenuse. I'm going to fill this in here. This 2 is the same as 2 over 1. And when I'm multiplying fractions, I go right across. So 2 times 4 times 3 gives me 24. 1 times 5 times 5 gives me 25. So the double angle here, so 2 times whatever this angle is, which means I'm really talking about more of this, double the angle, whatever that's going to be, is going to be 24 over 25. Okay, we'll see these. You're going to see some in your practice today as well as some of the examples above.